Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss Newton's rings and the measurement of wavelength and refractive index by using Newton's rings method. Let's begin. What is Newton's ring? A phenomenon in which an interference pattern is observed by the reflection of light between the two surfaces. These two surfaces, one is spherical surface and another one is the adjacent that is touched to that of flat surface. It is known as the Newton's ring. This interference pattern is observed due to the division of amplitude. In 1707, the scientist Newton observed that when the air film is formed between plano-convex lens and a plane surface of glass, one is plano-convex lens, another one is plane surface of glass, in between these two a air film is formed. Due to that, concentric bright and dark fringes, concentric bright and dark rings centered at point of contact between the two surfaces, and these concentric bright and dark fringes are observed when that is viewed with monochromatic light. That is observed when a monochromatic light is incident on that of surface. Just like this, here is the dark one. Alternate dark and bright fringes are often look like this structure. Again, let the central fringe is bright, so dark, bright, dark, just like the fringes are obtained. Before Newton, another scientist whose name was Robert Hooke, in the year 1664 was first describe that particular phenomenon, but he can't explain why the alternate dark and bright fringes are obtained. But Newton explained the exact reason behind this as the constructive interference, means the bright fringe is obtained between the light rays reflected from the two sources, and the dark fringe is obtained due to the destructive interference when the light rays reflected from both the surfaces. That particular reason was given by Newton. According to his name, the interference pattern is named as Newton's rings. Now we have to study what be the experimental setup adopted by the scientist Newton to get that type of interference pattern. That is its setup. A glass plate and a plano convex lens. This is the glass plate. Let G that one be the plano convex lens, let L. He used monochromatic source of light. For monochromatic source of light, example of monochromatic source of light may be sodium light. That monochromatic source of light, when collimated, use a conversing lens a convex lens is used, that L dash, it is a convex lens. So the light rays then use a glass rod, a glass plate which is used same material as that glass plate is placed here, that inclined at an angle 45 degree, that G dash, that is also a glass plate. So the ray from this source the angle is 45 degree due to we take the light rays are normal incident. The light is incident here, again on that of lower surface normal incident coming out. That is incident, further reflected back, coming out. Now we use a travelling microscope here. Here we use a travelling microscope. That one is travelling microscope. To observe what type of interference pattern is produced due to the Newton's setup, that is the plano convex lens and glass plate. Here the interference pattern we observed. Look here, this is the glass plate, that is the plano convex lens, that just look like a wedge-shaped film. In between this there will be some material, let air film will be there. So we obtain the interference pattern. Now we mathematically show what with the position of the dark or bright fringes, what be the conditions on which we obtain alternate dark and bright fringes, or we can say the interference pattern, or we can say the Newton's ring. To obtain that one, I just use that figure here. Let that be the glass plate. That be the plano convex lens. So the radius of that plano-convex lens, when I complete that particular circle, that will be the center of, let the radius of that plano-convex lens, that distance be r. Again that point D, that point A, B, C, touching point B, P. That distance also are the radius. And the thickness of that plano-convex lens, which is T, that is the thickness T from here to there, that will be the thickness. Within that of thickness, let me draw a circle. So the circle of a radius smaller, that portion be r, and that portion also r. BC and AB both are same in length. Now using the geometry, as AB into BC is same as PB into BD, using geometry, here AB into BC is equal to, AB into BC is equal to PB into BD, PB into BD, or AB is equal to BC, that is R, when a perpendicular drawn from the center to its one of the chord, then they divide that chord into two equal halves. So R into R, let we taking P as the center, that point as center, taking R as the radius, we draw the circle. Again PB can be written as PB into, in place of BD, that is PB PD minus PB, that is PD minus PB. Here we write AB is equal to BC is equal to R, or R square is equal to PB, that is the thickness T, into PD, that is the 2 times of that radius, which is 2R minus PB T. Look here, the radius is much greater than, as comparison to that thickness. So T is neglected, since R is much greater than T, then T is neglected. In that of expression, neglecting T, R square is equal to T into 2R. Therefore T is equal to, thickness T is equal to R square divided by 2r, that will be the thickness. Now we take the reflected light and observe the interference pattern. So, Newton rings by reflected light, Newton's it taken as equation number 1, rings by reflected light. We know that dark fringe is obtained in the interference pattern produced by the reflected light for normal incidence. For normal incidence condition, for normal incidence condition, because how the reflected light produce the interference pattern. Here is the system, is glass plate and a plano convex lens. When normal incident light is there, so some of the light gets reflected, one is transmitted due to that plate, again reflected, here transmitted. So, that reflected light, reflected rays superimpose with each other, produce the interference pattern, that is interference pattern due to that reflected rays. Due to that normal incidence, the condition for dark fringe, just related what be the condition for wedge shaped film for dark fringes, that is nothing, just a wedge shaped film. So, for normal incidence and relate to that of wedge shaped film for dark fringes, the path difference, that is 2 mu t cos r, here cos 0 is equal to 1. So, mu t, 2 mu t path difference is equal to integral multiple of lambda, that be the condition for dark fringes in wedge shaped film, where n stands for 0, 1, 2 like this. And for bright fringe, bright fringes, the path difference, that is 2 mu t is equal to odd multiple of lambda by 2, when that is a wedge shaped film. Now, you have to calculate what be the position of dark fringes and bright fringes. If you take, if Rn, that is the radius of nth order interference fringe, Rn be the radius of the nth order interference fringe, then the thickness t corresponds to the radius Rn, corresponds to the radius Rn, which becomes, so T is equal to, we take Rn square divided by 2r, that radius corresponds to the nth order interference fringe, since the thickness will be T here. Now substituting the above value of T in the condition for dark fringe, substituting the above value of T in the condition for dark fringe, we get dark fringe condition two mu T is equal to n lambda, 2 mu, in place of T we substitute, it is Rn square divided by 2r divided by 2 mu T, okay, 2 mu T is equal to n lambda, which implies Rn is equal to 2 cancel out, so Rn is equal to n lambda r divided by mu, it is under root, okay, that term is equal to n lambda, so Rn square is equal to this much, so Rn is equal to under root of that term. Now for air, refractive index mu is equal to 1, so that Rn is equal to n lambda r under root. This is the radius of nth interference fringe or nth dark fringe. Now what will be the diameter? Now the diameter that is represented by d of the nth dark fringe becomes d 2 times of radius, so d is equal to dn for nth dark fringe 2 times of Rn, which is equal to dn diameter of nth dark fringe is equal to 2 n lambda r under root. Similarly for bright fringe, bright fringe the diameter d of nth bright fringe is dn is equal to 2 times of condition for bright one, that is 2 mu t is equal to n plus 1 lambda by 2. By putting these values here, we have dn is equal to 2 n plus 1 lambda r divided by 2 under root, that will be the diameter for nth dark fringe, that will be the diameter for nth bright fringe. Now Using these mathematical formulas or using that Newton's ring experiment, we can evaluate the wavelength and refractive index. Let us be calculating measurement of wavelength. Measurement of wavelength. How wavelength of any light wave is measured by using Newton's ring. Here we use the concept for dark ring. For dark rings, the diameter d of nth is given by dn is equal to 2n lambda r under root. Similarly, for mth dark ring and for mth, this is for nth dark ring, that for mth dark ring, dm is equal to 2m lambda r under root. Now, squaring and subtracting, let equation number I, equation number double I. Now, dm square minus dn square is equal to square and then subtracting, we have 4 m minus n lambda r. From that of expression, so lambda will be dm square minus dn square divided by 4 m minus n into r. That will be the expression or mathematical formula to calculate wavelength. We have to require dm, dn and value of r. By putting these values, we can easily evaluate lambda. So, how to calculate dm and dn? Diameter for mth dark ring, diameter for nth dark ring. Generally, for calculation of sodium light, which is a source of monochromatic light, the rings are focused on the crosswire of the eyepiece and the microscope is moved extreme to the left of that of dark rings, and the crosswire is made to focus on any dark ring. Let that dark ring number may be 16th dark ring, and the reading is taken from the microscope, and now the microscope is taken to the extreme right side and calculating the similar procedure, first left then right. So, nth order means any kind of order, maybe 16th or 15th, what may be the order of that fringe is calculated, and that measurement, when we draw a graph, in that of graph, here x, y axis, in x axis let number of rings, let we take here nth order ring or mth order ring. In that of axis, square of the diameter d square. For nth order ring, let the diameter be dn square. For mth order ring, let the diameter dm square. Now joining this line, look at that figure here, that portion gives d m square minus d n square, and that portion of that of graph gives m minus n. Now putting these values in that of expression dm square minus dn square from the graph, that value from graph m minus n value, and we know the value of the radius, we can easily evaluate the wavelength. Next, measurement of refractive index by using Newton's ring. How we measure the refractive index of any material by using that Newton's rings method. So any transparent liquid, let it has the refractive index mu, which is to be measured, that is inserted between the lens and the glass plate. Here is the apparatus of Newton's ring, glass plate and the plano convex lens. In between these two, let we insert that material whose refractive index, that transparent liquid whose refractive index is measured. Let that refractive index, let mu. Generally we use the relation here m, that is the refractive index of the transparent liquid whose refractive index is to be measured, is placed in between lens and glass plate of Newton's ring setup. How to measure? For diameter of nth dark ring, here diameter of nth dark ring dn square is equal to 4 n lambda r divided by mu. Use the expression here for radius concept, then for diameter concept, due to that of refractive index, divide refractive index term mu. Similarly for mth dark ring, dm square 4 m lambda r divided by mu, that is the diameter of nth dark fringe, which is the diameter of mth dark fringe, diameter of nth dark fringe, diameter of mth dark fringe. Now squaring and subtracting. So dm square minus dn square, that with the diameter of, for what? The liquid having the refractive index mu, 4 m minus n lambda r divided by mu. That is equation number 3rd. Now repeat that process. Means the experiment again with the liquid is replaced by air in between the glass plate and the lens in that of Newton's ring setup. For air film, mu will be 1. For air mu is equal to 1. Therefore, d m square minus d n square for air, refractive index will be 1. So, the expression 4 m minus n lambda r, equation number 4. Now, dividing these two equations, therefore, dividing 3 by 4 we get, we have mu is equal to, dividing these two equations we have mu is equal to d m square minus d n square for liquid divided by d m square minus d n square for air. In the previous case, how we calculate dm square minus dn square, as we take the crosswire of the eyepiece extreme left and extreme and the right position, then calculating nth order and mth order and subtracting the square of their diameters. Similar pattern, first we take liquid and calculate dm square minus dn square, and then place air, calculate dm square minus dn square. Dividing these two, we can easily find out the refractive index of that of particular transparent liquid which is placed in between the glass plate and the lens of that of Newton's ring setup. So, with the help of this visual experiment, we understand what is Newton's ring, it is the experimental setup, and mathematically show the condition for brightness and darkness taking the reflected light. And by using Newton's ring setup, we can easily calculate the wavelength and refractive index, calculation of wavelength by using Newton's ring and calculation of refractive index using Newton's ring. So, with this useful and informative notes, let me wind up this session. Thank you.